In April 2025, a research team from the University of Cambridge published potentially groundbreaking evidence based on observations of the exoplanet K2-18b by the James Webb Space Telescope. The spectral data revealed something unexpected: signs of dimethyl sulfide, a molecule that, on Earth, is produced almost exclusively by living organisms. Is this the first real sign of life beyond our planet? In the depths of space, more than 1 million miles from Earth, the James Webb Space Telescope conducts high-resolution observations of distant celestial objects. Among the many stars surveyed by the telescope, a faint red dwarf has become the focus of particular interest. It is located in the constellation Leo, roughly 124 light-years away from Earth. Orbiting this star is the exoplanet K2-18b, a sub-Neptune-class world with a mass approximately 8 times that of Earth. What makes it especially interesting is its classification as a potential Haitian world, a type of planet that could host a global ocean beneath a hydrogen-rich atmosphere. Previous James Webb data already confirmed the presence of water vapor, methane, and carbon dioxide in its atmosphere, all of which support the idea that K2-18b might be habitable. But habitability doesn't mean inhabited. That's where the new observations come in. In April 2025, a team led by researchers from the University of Cambridge published new results based on infrared data from the James Webb Space Telescope. They analyzed light passing through the atmosphere of K2-18b using the mid-infrared instrument, short MIRI. This is the mid-infrared transmission spectrum of K2-18b. Each point shows how much starlight is absorbed by the planet's atmosphere at a specific wavelength. The dip around 7.5 micrometers is of particular interest. It may correspond to dimethyl sulfide, short DMS. The data matches a model that includes DMS, but the signal remains weak and uncertain. But why has this finding caused such a stir in the scientific community? To understand that, we need to look at how DMS is produced on Earth. It is primarily released by marine phytoplankton, which synthesize a compound called dimethyl sulfoniopropanate. While DMS itself is not directly produced by metabolism, DMSP can break down through enzymatic cleavage and release DMS into the atmosphere. Because this transformation is typically associated with biological processes, especially in ocean ecosystems, the researchers now speculate that the DMS detected on K2-18b could also originate from living organisms. But how reliable is the data? The signal has a reported significance of around 3 sigma, which suggests a possible detection, but not a confirmed one. To support this interpretation, the team used atmospheric retrieval models, which estimate the concentration of molecules that best explain the observed spectra. While the potential detection of dimethyl sulfide is fascinating, the results must be interpreted with caution. The relevant part of the spectrum lies in a region where the signal-to-noise ratio is relatively low and the signature is subtle. Experts have pointed out that alternative explanations, including instrumental noise or unrelated chemical compounds, cannot yet be ruled out. A recent commentary in Nature emphasized that more observations will be needed to confirm whether the spectral feature truly corresponds to DMS. So while this may be a hint of biological activity, it is far from definitive. In science, extraordinary claims require extraordinary evidence. The detection of dimethyl sulfide on K2-18b, even if tentative, would represent the first time a molecule predominantly produced by life on Earth has been observed outside the solar system. Its significance lies not only in the molecule itself, but in the fact that it was inferred from high-precision spectroscopic data obtained from a planet that may support liquid water beneath a hydrogen-rich atmosphere. For the first time, we are able to probe the atmospheres of potentially habitable exoplanets with enough detail to consider biosignatures, not hypothetically, but empirically. More data will be needed to confirm or refute the presence of DMS, but the fact that we can even raise the question with evidence is remarkable in itself. Whatever the answer, it will deepen our understanding of planetary atmospheres, of life, and of our place in the universe.